Okay, we might as well get started. To my Twitch viewers, welcome back to the stream. To my YouTube viewers, thanks for checking out this video. This actually marks episode number 50 of this series, which is pretty crazy. Been going on a roll, pushing this 5 times a week, Saturday and Sunday, then Monday, Wednesday, and Friday. With this stream and recording videos for YouTube, mainly because the project that we're covering is one that I really like to get done for myself. And that's kind of a bigger incentive to getting this project done and working on these videos at such a rapid pace. I am still planning on releasing the 3 other additional video series. Hopefully by the end of this month. I really, it's really taking a little bit more time with everything that's going on and working full time and everything, but hope to get those 3 going. The one will be another design series for another project. So that one's going to be kind of fun. I'm looking forward to working on that one too. But we have a lot to do to this guy and to the current board, and I'd rather focus on that as much as possible. If you are enjoying what we're doing, you like what we're doing, definitely like and subscribe. Hit that bell notification to be informed of when we drop new videos on YouTube. So, as we ended the last video, we were doing more of the board tests. We solved some problems. One of them was just me and my logic for the stepper driver had inverted logic on one of the enable pin. Once we got that worked out, the stepper motor started working. I just had to play around with micro stepping and all that. So there's going to be in the final code, there's going to be a lot of tuning between your PWM, duty cycle, frequency, and your micro stepping values. What your micro stepping settings are in order to actually get the motor to turn. It might take a lot of experimentation, a lot of trial and error. There are mathematical formulas you can use to figure that out. You Google and find the information to help you with that. But yeah, so that's where we are with it. So now we're going to continue our testing and throw together some test code to start working with the inputs. So we're going to slam together some basic GPIO test code to start testing the inputs for the control and the limit switch inputs. And it'll just be some basics to where it detects an input on that particular GPIO pin, and it'll just flash the status LED accordingly to the input that we're working on. So if we go back to the schematic, so we're going to be starting with the limit switches. And basically it'll flash once for limit 1, twice for limit 2, 3 for limit 3. Then we get to control be 4, 5, and then 6. So that'll basically what we're going to do, because we can use the same firmware to do the PLC testing interface. And that one's going to be a longer ride because we've got to throw together a PLC program to communicate with this. So I'm going to hopefully get the back to the board. So we've got the handy dandy little button box here that we're going to be using to interface with the board. This is going to be a pain in the rear. So we're going to be using the power supply's positive to feed the inputs. Since we're using the same power supply, we could theoretically take a lead off the common and bring it to the negative of the power supply, but we're not going to do that. We don't need to, because the way I threw these jumpers in here, you put the jumpers on the 2 pins, and that basically connects the common to the internal ground of the board. That way you don't have to worry about a common wire. And that's going to be for when we're working with like an external button that, you know, external buttons or inputs or limit switches that are just going to share off the same power supply, the same local power supply. So I've got this guy and I've got the negative. So one of the biggest things we need to avoid is tying it into common, because that'll put your positive straight to common. This is going to get slightly annoying. We don't need to crank these guys down too tight. Turn the power supply on. Now I don't have any code in here, so I don't know if you can see the red LED did light up. It's not very bright because it's not being driven all the way, and it still has the old firmware in there. We haven't done anything, but I got my handy dandy little button box. I'm gonna turn off the lighting on my bench real quick. Okay, I don't know if you can see that any better, but you might be able to see that my button box actually has an LED in it too that lights up. That does help indicate that, yes, the path is being made from, you know, the positive coming in through the switch and the LED into the opto isolator into ground. So that is validation that we do have at least the input side circuit completed. So we're going to switch over and we're going to try to get the first GPI to work. And then we're going to worry about the rest of it. So we're going to need to refer to the schematic, because I need to go, you know, make sure I have the right pins. I'm just going to drag this off screen because the main thing I want to focus on with this is writing the code. And so let's see here. So we're just going to clean some of this up. The LED is IO4. Now, let's go and get rid of this for now. So what we're going to do is define those top sets are my limit. We're going to just go LMT, LMT1, and come off the schematic. Limit 1 is IO35. We don't really need that. Okay. So the LED is going to be an output. We'll put together a nicer initialization routine. So remember, that's the red status LED. We don't need this LED. Again, this is Kickstarter. This is kickstarting code that I have. LMT1. Set that to an input. All right, so we don't need it printing that. I don't know why it's in there. I think that was just me. Again, we just want to make sure that we can actually, that our code, the basic logic works. So basically, we push that button. As long as the button's engaged, it's going to set that GPIO, the LED for the GPIO. It's going to set the status LED to high, which can be nice and bright red. So let's make sure we got us set up on the right COM port. You know what? It's probably mad because I don't have the TDI or the serial port plugged in. Now I should show the silicon, the Silly Labs. All right. So let's go and build it. Yeah, so we'll use the free RTOS. This will be kind of the majority of this video writing this code, because again, I want to be able to use it with a PLC. And so we'll write it in a way that makes it more usable, more functional for us. And just build and build and build. I try to cut out all the ambient noises as much as possible, so I apologize if things show up. Unfortunately for my viewers, I am human. And I do have to burp and pass gas in other ways. So I try to catch it, but I apologize if the mic catches it. I have to admit, again, I'm not sponsored by anybody, not paid by anybody, not paid to endorse their products, but I picked up a DJI wireless mic setup, and this thing is nice. It's one of their mini mic, I think is what it is. And this thing is freaking awesome for doing this. So, but the thing is extremely sensitive, and it does pick up a heck of a lot. So I've tried getting some filters running to knock it out, but I apologize if you hear stuff. You'll hear my chair creaking. I do tend to move around a lot to get more comfortable, and also so I'm not stationary all the time. You know, that's the biggest problem with engineering work, with PCB engineering and schematics and all that, is it's too sedentary. It's just you're not up and moving around that much. Other than the factory jobs, when I got into the technology jobs, they've all been like that. Ah, we compiled, so we're good to go. All right, so let's flash this puppy over. And we are programming. So, yeah, I might have to try to kick off some might have to start changing some of my shop lighting around, because unfortunately I'm doing what I can so you know the LEDs on the board don't get drowned out. But I also like having plenty of light, unfortunately. So the good thing is the status LED did shut down, or did go off. Now we push the button, it comes on. Yeah, see, it's nice and much more brilliant now, because now it's being fully driven. Before it was like an undeterminate state in a gray area because the pin didn't know what it was supposed to be doing. But now that we have a defined GPIO level and status and what it's supposed to be doing, yeah, it's nice and bright. It's maximum brightness. Mind you, again, that's half the current. I think, 10 milliamps, I think is what we calculated it for. That's half. So we can reduce the value of the resistor, the current limiting resistor, a little bit and get that thing even brighter. But, you know, I don't like blinding myself. I like nice bright LEDs on boards, but I don't like blinding myself. So there we go. It comes on when the switch is pushed. And when you let go of the button, well, the button is pushed, you let go of the button, the LED goes out. So that input 1 is working. That means the ESP32 is working exactly as we intended. But because of what we want it to do, we want to be able to be a more functional test and to validate which input is pressed or active. We're going to have to do some more kung fu here. So come back over to here, and we're going to kind of clean this up. Now I'm going to go through, and we're going to all right. Keyboard wanted to be stupid. 2, 3, 1. Let's go just CTL. 2, 3. All right. So what I'm going to do then is, actually no, let's fix this. The LED can stay that, because what I'm going to do is we're going to make this kind of more proper. All right. So this is what we're going to do. I don't want to complain to me. So we're going to actually do it right. Okay. Because I want to use the same initialization routine I used in that other. And I think it'll get mad if I don't define them as integers. Okay, limit 2 is equal to IO36. Limit 3 is IO39. Control 1. $32. Over there. 32, 33, 34. Okay, so now we have our input. I don't really need this. It could be a little bit sloppier code. All right, but you know, that's fine. Coding maestro here. So what we're going to do, all right, wait a minute. Oh, no, don't tell me. Oh, let me check something here. Pardon me, my friends. Oh, I thought the battery in my keyboard, my wireless keyboard was going bad, but I think my wireless keyboard as a whole is going bad. So what we're going to do here, copy that. And what we're going to do is just go through here and all right, so now we have that. Those are all inputs. LED. You know what? And all right. All right. That way everything kind of matches. Everything's nice and cute and organized. So, okay. So, we're going to copy this under app main. All right. Boom, 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 boom. Okay. So that sets up all the inputs. So iterate through that. Yeah, I could hardcore define this, but the great thing about kind of leaving it open, for one thing, we have plenty of memory in the ESP32. And I think there's no real reason to for this. That way we could just keep expanding this without having to keep changing that number and automatically pull all this. Boom, boom, boom. So this will actually run through, iterate through, and initialize all those GPIOs in one shot without having to type a billion different things in. All right. So I don't like to flow my code like this. I prefer to do it. All right. All right. Okay, let me make sure I've got the right. Make sure I've got it here. All right. Okay. So we want it to be on. So if GPIO is on, we want it to be on for half a second. And so basically we want it to be on for half a second, off for half a second, and then basically kind of reset within this loop as long as the button is pushed. So let's build this. Let's make sure it does compile. All right, so far it hasn't peeked its guts out, so let's flash it over. Go back over to here. Indeterminate state while it's programming. That's why it's that. It looks like it flashed. So okay. So what in the world is going on? All right. Oh, I know what I did wrong. No, I'm a goofball. So I never actually never actually configured the LED GPIO. Okay. Maybe. Put. All right. And never actually set the never defined and configured the LED. I'm bad for that. So it's gonna compile. Go back over to here. You know, if I kick those lights off, they might make it too dim in here to work with everything else. So we'll just have to deal with it, I guess. We're gonna flash it. Now the LED should go off. There we go. So hold the button. There we go. So it's flashing. Roughly half a second on, half a second off, half a second on, half a second off. Roughly. So that would be the... Well, what we're going to do is we're going to make sure we clearly define that the off period will be longer. That way it's even more defined. Because then I think what we'll do, well, I'll show you what we do when we get there. But let me get this, let's get this flashed, compiled and flashed and tested real quick to verify that it will work as I intend to. Blah, 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 boom. Okay. So it should come on and then basically a single flash and stay out for a longer period of time. Okay, perfect. That does exactly what I want it to do. So let us go back to here. And this is where it gets... limit equals 2. Or no, limit 2. So... nope. We want it to... okay. We want it to flash, wait, go off. Wait. Flash. Yeah, I'm sure there's more elegant ways to do this. But you know what? I don't really care about slop. So if limit 2 is engaged, what it should do then. So limit 1 is flash, be off for a period of time. Limit 2, it'll flash, flash, turn on, turn off, turn on, and then, okay, well, let's test it. We'll have to move the switch over, but that's not a problem, the button over. We have the technology. And the good thing is once this code's written, it'll be portable and usable. It's just going through this iterative process and getting things to work. Time consuming. There we go, programming. All right, so we're over. So we should have the single flash, long period off, single flash. Now, so one of the things I'm kind of, so it should be flash, flash, long period off, flash, flash, long period off. All right, perfect. It is working as we intended. Beautiful. So with all this in mind, not to get too distracted, but so one of the things that I also like to work on my head while I'm working on, even at places like this, is looking kind of thinking about ideas of moving forward to actually building a test jig, like a test fixture to test these for production testing. And I was thinking of, so if we go back to the camera here, so having probably designing 3D printing something that can hold the board. And obviously we want to be able to kind of index it and just hold it in place. So what I was thinking about, let me go over here, is getting a set of these, mainly because it's variable, multiple different sizes in here, but the 3mm to use as basically create a test jig, press fit, obviously cut lengths of the 3mm diameter into holes. That way we can slide the mounting holes over and the board will be in a test jig, secured properly. We can plug in like pre-wired cables, maybe have like the controls like down here, like button box or something. Like, well, not buttons or not a button box, but like instead of like a button like this guy, use like the smaller tactile momentary buttons. They don't need to be special for this. This is just because this is what I had at the moment, and I was able to just throw this little enclosure together, and you know, come on, it's like the perfect fidget toy. Perfect fidget toy. Yeah, that's just fun. It's fun to push those buttons. And then things like that way you can maybe have the stepper motor already pre-wired, have a fan assembly pre-wired. You can just plug everything in. Even something with RS-45, and you can just use a computer, flash one test routine and just go with it. So those are some ideas, some things we can consider. That way, for production testing, we'll have our test firmware, and then we'll flash the out-of-box firmware, do some real quick testing with that, whatever we can do, because obviously it's going to be out-of-box. But yeah, so that's the thought behind what we're doing. That's just how my mind works. I like to bounce between ideas. Okay, 3. And everything's just going to grow accordingly here. So we're at the off stage. Wait. And the code is growing. Now that I think about it, I could probably come up with like some kind of iterative loop, based off of what limit it could go up, and like set a flag and possibly run through some kind of iterative loop, like a do while, which is not a problem. I mean, it's perfectly fine. We can figure all that out. I'm not too worried. Again, this is just some bench testing code, and I really don't care. The main goal is to get the code on the ESP32 to do the subsystem test. So that's 2 blanks and then a long pause off. So if we come over here, tie it into the last limit switch input. So we should have 3 flashes and then long pause off. 2, 3, long pause off. 1, 2, 3, long pause off. And then, yeah, see, that's why a good test jig will be instrumental long run. This is not sustainable for actual production level testing. Having to disconnect and reconnect, it'd be just much easier to have the pluggables already wired in with a test jig. And then that should be, yep. All right. So far, so good. Everything's working. None of the limit switches seem to be interfering with each other because that's only blinking once. Now we're going to go down to the control inputs. Are these guys still isolated? Obviously, this LED is on and the button, but nothing's happening. So obviously the circuit's working, but nothing's cross-talking, which is beautiful. So we're going to copy this guy. Yep, that's messy code. Make fun of it. I don't care. Now we're going to go CTL1. All right, so now we need to add another one of these. Waits. Turns it off, waits, and then turns it off. So. Wait. Okay. So now we're at 4, so it should flash 4 times. Iterating on all this is just so much fun. But again, once we get the PLC program written, who knows, maybe we'll get kind of a start on that today because we're actually jamming. Well, maybe. I still have the temperature sensor to work on. Because this at least validates these inputs up to that point. All right, so it should be flashing 4 times. 1, 2, 4, then a long pause off. All right. So. All right, so that is working perfectly. That is beautiful. Obviously, with the V-test delays and all that, The PLC program's gonna have to be, it's just gonna have to kind of delay longer between switching between each control, but that's fine. We'll accommodate, we'll make it work. Now we need control 2. So we need to go on, off. One more. Oops, forgot this. It's getting really sloppy. It's becoming super sloppy. But I don't care. We've only got one more to write. And yeah, I could have just slammed it all together in here and tested it, but sometimes it's just too much of a pain in the rear. So we're still connected. I'm going to wait till it gets done flashing. All right. So that should still be what, 4 times? 1, 2, 3, 4. Long pause off. All right. You see, it's going to finish it out even though I let the button go because I'm using the VTAS delays. It's fine for what we're trying to accomplish, what we need to accomplish with this. 2, 3, 4, 5. Long pause off. Maybe we'll work on tweaking it out, depending on how sloppy, how horrible it is to work with the PLC. But so 1, 2, 3, 4, 5. Long pause off, and then cycle repeats. And it'll keep going until even after I release it, because like I said, it's using the VTAS delays. It's kind of stuck in it. So we'll solve that problem if it becomes a problem in the for the PLC test. But we'll have the foundational code in here, and we know the ESP32 works. So let's get the last control input, which is control 3. So we're gonna need that. Delay, turn it back on, delay, turn it back off, and then delay the big one. So that should be 6. All right, so let's flash this guy over. Boop. Flash this guy over. Now, if things work properly, we should have 6 flashes and a delay. 2, 4, 5, 6. Oh, maybe I miscounted. 2. Okay, hold on. You know what? Nope, it won't work. So it's actually working as intended, because I wasn't on the right input. See, there we go. That was me being me. 3, 4, 5, 6. There we go. Now it's working. 3, 4, 5, 6. Long pause. All right. Boom. So this is a very good positive thing. And then what I'm going to do is remove the jumper off the common and validate that no, it doesn't work. So without that common there, there's no return path. And rather than having pluggables pre-wired. 2, 3, okay. And then pull the return path off. Nothing. So that works as intended. Wow, that makes life so much easier. All right, so that is a good thing. I'm going to turn this off for a second. That way we don't accidentally fry anything, because with the inputs, we're kind of technically done at this stage. The little button box. served its grand purpose. And we'll be kind of, wiring will be kind of bundled up. I don't know about you, but I've got a habit of saving the little twisty ties that come with like cables, like USB cables and HDMI cables for things like this. Makes life so much easier. So I'm going to put this guy on top of my bench, get it out of the way. Okay, so we have a choice. Do we start working with the PLC inputs, that's going to take a while, and maybe we could devote tomorrow's video stream for it. So let's see if we can get the temperature sensor working. Let's see if we can get anything off of it. That might give me a headache because it's ADC and me and ADCs don't mix very well. But at least what we can do is wow, I mean, we are jamming quite along. And this is, so far, so good, extremely positive. So all the actual subsystems within the board, within the design, so far are working. Now, technically, we don't have to do this, but I want to do this because of the common for the limit. I want to actually be able to test it to make sure it does work as an independent input, regardless of, that way it's isolated, an isolated input. That's basically what it'll be. So now let's go ahead and kind of look at the temperature sensor. So do I have anything in here? No, I do not. So what I'm going to do is I'm going to do my normal, get rid of that, get rid of that, get rid of that. Don't really need to git ignore. I'll make sure I clean everything up. Don't need that open. Now, all right, so I'm going to open up another thing I started working with, just to give me a little bit of a head start with getting the ADCs configured. I'm going to open this guy up. Test. So, don't care about that. This will eventually quit complaining, go away, go away, go away. I probably forgot to rename that in the other one, but that's fine. All right, close that guy. All right, now we'll go to main. Okay. Don't need all that. Close that, close that. Okay. All right. So, don't need GPIO. Leave string there for now. But we do need ADC. ADC. Let's grab this stuff. Really don't need any of this. Not using any GPIO garbage right now. Get rid of this garbage. That has something in it to look at. So, oh, one of my other cats has decided to come up and say hi to me while I'm doing my stream. And unfortunately, you're on the wrong desk. I don't have a camera to look at you. You can just see her purring and staring at me. Okay, voltage converted. I think I might need that. Not sure. Maybe not. I don't know. Okay, we don't need that function. All right, you know. Main. All right. Did I even tell you what pin you're on? No, I did not tell you what pin you're on. All right, don't tell me. All right, ADC rule. Don't tell me I'm using the internal. I'm hoping that I'm using a pin that's not capable of ADC. Maybe that is something dumb I did. Because where am I? ADC channel. Okay. Okay. Well, so I might have to use one of the other ADCs in here. So let's see here. What GPIO did I set up for that? IO2. All right, ADC channel. Okay, let's see ADC. All right, cat. All right, ADC channel. Zero. All right, so I need to pull up the data sheet. All right. Now's the data sheet. So I am being an idiot. ADC. Pull up the data sheet. Okay. Okay, so we are, according to this, we are IO2. So if we go here to the ESP32 data sheet, IO2, GPIO2, so ADC2 channel 2. ADC2 channel 2. AC2 channel 2 is GPIO2. Oh, ho, ho. All right. Okay. Okay. Good. not worried anymore. Not worried anymore. I knew somewhere. I knew you had to check that out. So what we're going to do is we're going to at least see if we can get a raw value. And it'll probably be written ABC 2 get raw channel and copy this. There we go. Now, because I don't want to all right, this guy back open. Wrong one. Jeez Louise. Got 1,001 things going on here, and not one of them is good. That's not what I was looking for. My goodness. I'm so disorganized. Way. Just open up the original one. Mainly because I can never remember. I can never remember. And that's fine. Don't need that. All right. Get the delay off of y'all. Clean this up. Well, this crap. Don't need that. Double line between it. Oops. 2 new lines. That way I don't have to worry about it. All right, so we're just going to use the internal. See if it builds. Oh, why do I have this still in here? Get out of here. Wait a minute, that's not even the one I wanted to work on. Oh my God, I'm going to shoot myself in the face one of these days. What in the world am I doing here? Here we go. Oh, VS Code, I hate you so much. I hate you so much. Are you kidding me? Yeah. It wants to be so slow. That I accidentally broke. Because it wanted to. That's what it did. Okay, VS Code. Don't you dare be. There we go. Way, it's easier to look for stuff. All right. All right. Oop. Two lines. So we want to see if we at least get an ADC value off of it. Will you compile? And we should see it down here. Let's see if we at least get an ADC value. All right. And then we'll just have to suss out this code to get it converted over. Take the voltage value because it'll be in millivolts. Well, the ADC, raw ADC value, then we'll have to convert it over based off of the attenuation and the bit width, which should be, and then get everything set up for the 3.3 volts reference. Or I can't remember what reference. So we'll have to get all that set up and then get all the conversion done. All right. Oh. But once we can do that, then we can get it close to measuring voltage because it'll be in millivolts. So like 1,000 millivolts will be 1 volt. And we'll go off of that and kind of figure out how to do a table. Because I think the data sheet said that, this voltage is this temperature. Having that for a reference, it would be easy to kind of make a kind of like a map. Kind of map it between temperature ranges. So the less voltage it puts out, the colder it is, basically. So we could just use a basic map function. Simple. And since it's a 1-to-1, X number, I think it's 10 millivolts or something like that per degree Celsius or something like that. It's a linear. What did you? All right. ADC2 get raw. What are you mad about? Too few arguments. ADC get raw. All right. ADC2. Oh, okay. Or a single channel. Okay. So should that work? Or are you going to puke your guts out and say, hey, you're an idiot? Well, you're worrying about legacy drivers for the ADC, so we might have to look into. Okay, all right. So should every 2 seconds. So we're going to flash it. And then monitor. Oh. Quit being an idiot. All right. Now it should flash. See what this guy says. All right. Getting nothing. All right. Like ADC one shot. Legacy of drivers depreciated my. So we probably have to go over to the ADC one shot driver to get this to work. So we'll have to look into how to do that. So I will probably have to create an example because since it's depreciated, this probably will not actually work. And it will not detect anything. Yeah. Because at room temperature, there should be a voltage there. Are we actually on the correct GPIO? Let me double check. Temp sense is IO2. IO2, GPIO2. Yep. So we're on the correct GPIO channel for ADC. I think we're going to have to switch over to the one-shot ADC driver, which will take a little bit, and we'll work on that tomorrow because we're already heading towards an hour with this video series. And it's already been a long day for me with the other projects I'm working on for work, for my job. So I'm gonna have to call it here. Just we've got a lot to do. We've got to get some new code. Probably throw together pull up their example for their ADC one shot with this newer SDK, and kind of get it rolled in and incorporated and figure out what we need to do. Sort out their example code and make it just simpler so it can be bare metal without having to use the ISP and the IDF configurator, basically. So yeah, it's getting 0. So I wonder if just the fact it's been depreciated, it's just not going to work. All right. Well, I appreciate you tuning in and checking out this video. We've made more progress. We've validated that the inputs do work, at least with the common tied to the internal ground. So that is a very big positive. We've got test code that we'll be able to port over and also use with the PLC. So we've got a bunch of tests to throw together and finish up this weekend. We'll try to get this ADC taken care of tomorrow. Depending on how smoothly that goes, we will then start working on the PLC programming to test the inputs using a PLC. That way we can validate that it does function properly on that. So I thank you for hanging out with us and checking us out, and I will see you tomorrow. Have a good evening.